said 5 are submitted, and so you can see that I already did yours. Does that count?
How do I know that's you? Is your name anywhere on there?
No, it didn't print on there with it, so.
Okay. All right.
I mean, those. You want to see my schedule?
Okay.
Those are my
All right.
classes.
All right. Let's get started. The
It didn't print out my name either.
Okay. Oops. So we're coming up on the test next Wednesday. Don't forget the test review is posted, right? I still haven't worked the answers yet. Probably won't get around to that till this weekend. But the test review is posted on the Blackboard page. And since we still have some topics to cover today and Wednesday, today and next Monday, then, I think the test review this time is really going to be important. So I would take the time to, definitely take the time to, as always, to work the test review, right? But especially for test number 3, and we won't get a chance to go over that test between the day we take it and the final exam. And the final, which is on May the 11th, and the final exam is comprehensive, right? So the test review is especially crucial this time. John, do you have a schedule for test review this time? Yes.
It's going to be on Friday from 10 to 12.
This Friday from 10 to 12? Okay, yeah. So this Friday from 10 to 12, that will be our test review, and then I guess you have your regular time on Monday as well, right? Okay, after class. So next Monday after class. So there are 2 chances to review with John for the exam. So for some of you, that exam is the exam number 3 is really crucial. If you have a low exam score, that exam number 3 will be really crucial to you. So really take advantage of the printed test review, and then also reviewing with John. So I'll post that the times there in an announcement of when John's test review is when I get back to class. So don't forget, registration is open, right, for the fall semester, okay, and summer. So here's your chance to get registered, get advice, and get registered for your classes for summer and fall, so you can get into the best schedule possible. And don't forget, if you bring me your printed receipt for your course evaluation, that you've done your course evaluation, then that's worth some currency. That's worth extra credit, $5 in your currency account, right? Okay. And next Monday, I will give you your shopping cart form so that you can use to spend your currency, and then you'll bring that back to me at the final, so that I can then add whatever points there that you're going to use, right? Or however you're going to spend your currency. So I'll give it to you on Monday, and then you bring it back to me at the final. Then you want to email me that back, okay? And there's an option on there to buy out the final. So if you're going to buy out the final, you'll have to email me that back before the final, okay? Email me that back before the final, that you're going to do that, okay? I'm also passing out, or Johnny's going to pass out here in a few minutes, another extra credit assignment, okay, which is written on paper. And so we'll be talking about that, how to do that today. I hope by the end of the class, or if not, we'll have to Monday. And so that will be your final chance for an extra credit assignment to add into your calculus currency, okay? And then you've also got, of course, the attendance policy, so that could yield you $15. And then also, depending on your exam 3 score, you might get some currency for that too. And your homework average, right, also will contribute possibly to your calculus currency, but I won't know that until the end of the semester.
Are the quiz currencies already in?
No, so what I did was, since we only ended up getting, I had a problem making up quizzes this semester, finding sufficient number of homework problems for the quizzes, because I didn't want the quiz problems to be the same as the homework problems, and this book doesn't give a lot of problems. So I deleted the quiz category. So the two quizzes, we only had 2 quizzes. Okay, one of them was extra credit, but we only had 2 that counted for a grade. So those I have moved into your homework average. All right. So you now have, I think there's 13 homework assignments so far. Okay, and something like that. Okay, and so those 2 have gone into your homework average, and so your homework will count 19%. Because the quiz plus the homework was 19%. So altogether, your homework is 19% of your total grade. So I've already updated the grade book to reflect that. Okay? All right? Yeah.
You won't get the currency for the quiz average if you have like more than 85%?
No, you won't get the currency for the quiz average, right? Yeah. You'll get the currency for the homework average. Okay? All right? So I may so we may give a little bit of extra currency for the homework average. I forgot what it was now. It was X dollars for 80 and so many dollars for 90 or something like that.
It's like 5 and 10.
5 and 10. Yes, I may bump that up a little bit. Okay, the amount that you get. So you've still got 4 homework assignments left, right? Okay, 4.2, that was due tonight. I moved that back till tomorrow. That seems to be pretty easy for most people. The people who have worked on it have really high scores on that, so I moved that back to due tomorrow night. And then you've got homework 4.4. This is about inflection points due on Monday. And then those final 2 assignments, because the test is May the 4th, so we've run out of time. These aren't lengthy assignments, but they're both due on Wednesday of next week. Okay, so in addition to the test review, don't forget to be working on your homework assignments, right? So you want to get that finished prior to the test, because that will help you prepare for. That's another way, of course, to help you prepare for the test. All right, okay. So those can also bump up your average, although we're getting quite a few assignments now, so it's harder to move your homework average than it was earlier in the class. Okay. Let's continue talking about integration. So that was the subject we started at the end of class last time. So remember, integration refers to determining the area beneath a curve down to the x-axis, all right? And there's some kind of unusual notation associated. That's the process of determining that area is called integration. And there's some kind of unusual notation that's very old, okay, that is associated with this process of integration. That indicates that we use to symbolically indicate this area, because we can't always draw these areas on the screen very easily. That's kind of clumsy sometimes, right? So we do have a mathematical notation that we use to indicate an area, okay? And usually these areas are not easy to determine because we're trying to find the area beneath a curve down to the x-axis. So unless the curve has a very friendly shape, okay, one side of that area is going to have an irregular edge to it, right? Okay, like in this picture, and that's what makes the area difficult to determine. Okay. Today we'll look at some examples where the curve is a very simple curve, where the area is easy to determine just using geometry, okay, but just using our knowledge of geometry. But typically, since curves have all sorts of wiggles in them, that makes one side of the area irregular, and that's what makes this problem challenging. All right, of determining an area or carrying out this integration process. So remember, we learned this notation last time. Once you've seen it a few times, it's easy to understand the notation, but that doesn't mean that it's easy to evaluate the notation, okay? So the formula for this particular curve that I have drawn here, that's the blue curve here, right? That happened to be x cubed minus x squared plus 4x plus 12. So if we wanted to indicate the area between that curve, all right, down to the x-axis, so we're always determining the area between the curve and the x-axis. So down to the x-axis, so this shaded area that I have indicated here, between minus 1/2 and 1.5, and I just chose those limit values just for this example. Okay, there's nothing special about those limit values. The way we would indicate that area symbolically is we would use what's called an integral sign. So this is called an integral sign, and it's elongated S. Okay, the reason we use an elongated S is this is supposed to indicate sum. All right, okay, and which of course the word sum begins with the letter S. I'll show you why sum, the idea of addition, is involved in this process of integration in the last couple of examples we do in these notes. Okay, so we have this elongated S, this integral sign, and then on the top and the bottom we indicate our so-called limits of integration. So these are the boundary values for the area on the left and the right. Okay, on the x-axis. So these are values on the x-axis. So again, this area is starting at minus 1/2 on the x-axis, so I put that as the lower limit. So we use the lower subscript there. And then this limit on the right, this area stops at 1.5 on the x-axis, so I'm going to put that as the upper limit, or the superscript here for our integral sign. And then we just put the formula for the curve, or you can put the name of the function. So I also could put f of x, because that's the name of this function, behind the integral sign. And then you terminate this notation. This is kind of like a grouping symbol, but instead of using a bracket or a curly brace or a parentheses, which is a normal sort of modern way we would terminate some sort of expression, we use kind of an old-fashioned notation. We use this these two letters dx, all right? And that does have some mathematical meaning to it, but for our purposes, we can just think of that as sort of terminating this expression, all right? Just showing us where this expression, where this integral stops, okay? So again, this whole thing is referred to as an integral. This is an integral sign, and the process of evaluating or giving a value to this expression, that process is called integration. And the value of this expression will be exactly the area here that I've got shaded, okay? Notice that's an area, so it's going to be in square units, right? Because that's how you measure area, two-dimensional area. You measure it in square units, right? So the units of measure for this integral will be square units, whatever that value turns out to, whatever that area value turns out to be, okay? All right, so that just a quick recap of how far we got last time, all right, talking about this integration process. And today we're going to look at a few examples of actually trying to carry out this integration process, of actually trying to evaluate one of these integrals, okay? And we're going to start, of course, by doing it approximately. And then I'll show you next time how we can do this exactly, okay? And it turns out that you can calculate these areas precisely. In many cases, you can calculate these areas precisely. And it turns out to have a very strange relationship to differentiation, which is our first topic, of course, that we've spent the whole semester studying, okay? So that's why integration is part of the study of calculus. Okay? All right. So stop me now if you have questions, because I'm going to be talking kind of fast here today. Yes? Square units, right? Okay, because when you measure a two-dimensional area, right, like the area of a rectangle or the area of a circle, it's the unit of measure is always square units, right? Okay, like when you're measuring the size of a room, it would be in square feet or in square meters, right? Okay, this is the same idea. Okay, I just didn't indicate how the x-axis is marked off here. I don't know if that's in feet or inches. It doesn't really matter. Okay, it's just some sort of arbitrary unit. So the unit of measure is square units there. All right, let's actually calculate one of these integrals. Okay, and because this one is, the curve here is very simple, we'll be able to do this with geometry. But normally, in general, right, the curves won't be so easy, and so we won't be able to use our knowledge of geometry to evaluate these integrals. All right, so when you look at that integral, remember that is representing an area. Okay, so the first thing you want to think of is, oh yeah, that's an area, right? It looks like a very imposing mathematical expression there, right? Okay, but in the back of your mind, just keep in mind, oh, it's not so bad. That is just an area. That represents an area. It's the area beneath this curve, which happens to be a straight line. 6 minus 2x is just a straight line, okay? So it's the area beneath this curve down to the x-axis, starting at 0 on the x-axis, so starting right here on the x-axis, and then going over to 3, which in this case happens to be where that line crosses the x-axis, okay? But it doesn't have to stop where the line crosses the x-axis, okay? That's just convenient in this case, all right? So in other words, we're trying to figure out what's this area right here, right? From the curve, starting at 0, going down to 3, beneath the curve down to the x-axis. So we can shade that in, right? So we can remind ourselves of what area here we're trying to calculate. So in this case, our area has a nice regular shape, right? In this case, our area is just a what? What's that thing called? Triangle, right? Yeah, that's right. That's just a triangle. So if we can remember the formula for calculating the area of a triangle, then we're in business, right? Okay? Because here we're just trying to find the area of a triangle, okay? All right, so just to remind you, here is how you find the area of a triangle, okay? It's pretty simple, because a triangle like this is half of a rectangle. So what you, right, is see if I drew a rectangle out, if I double this triangle, right, okay, across and down like this, then this triangle would be half of that rectangle. So the way you find the area of a triangle like this is you take the base times the height. So the base of the triangle is this portion here, this horizontal portion of the triangle, right? And then, of course, the height of the triangle is just what it seems to be, right? Okay? It's how tall the triangle is, right? So you multiply the base times the height, and then you just have to take 1/2 of that, okay? Because if you multiply just the base times the height, you'd be finding, if you multiply just the base times the height, you'd be finding the area of this rectangle, okay? Right? But we want half of that rectangle. That's the triangle that we're interested in here, okay? So let's see, what's the base of our triangle in this case? What's this length? 3, right? That's obviously 3, right? Okay? Because we're going from 0 to 3 on the x-axis. And the height here, that's pretty easy to see also. That's going to be just what? 6, right? Okay? This isn't drawn to scale, so it looks like 3 is more than 6 in this picture, but that's just the way the axes are marked off, right? Okay? Yeah, so the height there is 6, so we know then that this integral, really easy to calculate, it's just 1/2 6 times 3. So let's see, 6 times 3 is 18, right? And 1/2 of that would be 9, okay? So that integral is just 9. If we have to give the unit of measure, it would be 9 square units, all right? Whatever these units are on the x-axis. So those could be feet or inches or meters or centimeters or something, okay? In most mathematical problems, that's not really of crucial interest to us, okay? All right, so see, sometimes not that hard, okay, to calculate one of these integrals, okay? Of course, but in this case, we just got lucky because this curve, 6 minus 2x, just happened to be a straight line. So that made the problem kind of artificially simple for us. Now, you may be wondering here, what happens if the curve goes below the x-axis, okay? Because curves are not always above the x-axis, right? Sometimes curves dip below the x-axis. So let's think about calculating this integral, all right? And here I've got the same curve now, which is just that straight line, 6 minus 2x, all right? But now I want to find the area from 0 to 4, not just from 0 to 3, but from 0 to 4. So when you go from 0 to 4 here, see, part of that curve dips below the x-axis, okay? So now we're trying to calculate this area, which we already had calculated a moment ago, right? We know that it was 9. I'm talking about the area over to 3, right? But now we also have this little piece right here from 3 to 4. And again, it's always between the curve and the x-axis. Always between the curve and the x-axis, all right? So we're also trying to find this area of this little piece right here, okay? All right, now, here's the one unusual thing you need to remember about a mathematical integration, okay? The areas beneath the x-axis, we're going to count those as negative, okay? So areas beneath the x-axis, we're going to count as negative. Areas above the x-axis, we're going to count as positive, just like I did in the previous example. But areas beneath the x-axis, we're going to count as negative. Now, normally, in geometry, you never think of an area as being a negative value, right? Okay? But in integration, you can think of areas as being a negative value, all right? So what I'm going to do here is calculate these two areas separately, but I'm going to count this one as positive and this part as negative. And then to find the entire integral here, the value of the entire integral, I've got to sum up the negative and the positive pieces here. All right, so let's see. This should be pretty easy, though, because both of these pieces, remember, I'm going over to 4 here, right? Okay, which is right there on the x-axis. I covered it over, but there's 4 on the x-axis. Both of these pieces, though, are just triangles, correct? So I can find both of those areas pretty easily. So we already know what this big area was. That was 9, wasn't it? So I don't have to redo that calculation. So I know that's going to be 9. And now let's find the area of this little triangle right here, okay? All right, so let's see. What is its base? So what's that? That's the length? 1, right? Because that's from 3 to 4, right? So its base is 1. Well, first we're going to calculate it as just an area, and then we're going to put a negative sign on it, okay? All right? And then what's its height? 2, right? Its height is 2. And so then you take 1/2 of 1 times 2, right? Okay? So that's the area of this triangle. But again, since that's below the x-axis, we have to count that as negative. So instead of adding that to the 9, I'm going to subtract it from the 9, okay? So the total value of this area turns out to be not 9 any longer, but let's see, what's 1/2 of 1 times 2? That's 1, right? So this just turns out to be 8, okay? So that seems a little bit counterintuitive, right? Okay, we have a bigger area here shaded than before, but notice the value of the integral turns out to be less than before, okay? It turns out to be 8 instead of 9. But again, that's just because areas beneath the x-axis we have to count as negative. So that's sort of the one little exception there where integration is a little bit different from geometry because in geometry you never have negative areas, right? All right, so the value of this integral is 8. So we've done it again. We've carried out integration. When you actually take one of these integrals and evaluate it, that process is called integration. And so we've carried out this integration, and we've determined it's 8. Again now, kind of simple, right? Because we had just a very friendly curve here, right? And so we could apply our geometry skills to evaluate that particular integral. So I skipped over this part of the notes, but this is exactly what I just was explaining to you, okay? Sometimes integrals can be negative, okay? So in calculus, we can have negative areas. Not in geometry, but that's possible in calculus. Wow, let's try another one here, but this one is going to be very abstract, okay? All right, so here I've got the function x cubed minus 6x squared plus 4x plus 5, okay? All right, so if we're going to do integration with x squared minus 6x squared plus 4x plus 5, that's going to be tough, all right? So that's going to be much more complicated because here we have, you know, a nice wiggly curve, right? Okay, here we've got a wiggly curve. So calculating integrals with that curve is tougher, okay? But at first, in thinking about this, all I want you to tell me is whether the integral is positive or negative. So you don't have to tell me exactly what its value is. Just is it bigger than 0 or is it less than 0? Or it could be exactly 0, okay? That's another unusual thing about integration. You can have integrals that turn out to be exactly 0. Usually don't have 0 areas in geometry, but in calculus you can have 0 areas. All right. So let's start with the first one, A here. So here we're trying to find the area from 0 to 1 beneath this curve. Okay. So let's just shade that in. The area from 0 to 1, so there's 1 on the x-axis, right? And we're starting at 0, so we're talking about that area right there is what corresponds to this integral. So again, if we were actually trying to calculate that, that would be tough, right? Okay, because you know the top portion of that area is this curve shape, right? But all I want to know is it positive or is it negative? So is that going to be a positive area or a negative area? Positive, sure, right. Okay, so that integral will be positive. Positive is greater than 0, right? Okay, so I don't know exactly what the value of this integral is, but it's some number bigger than 0. Okay. All right, well, let's continue here. So what about if we're going from 0 to 2? All right, so there we're extending the area just a little bit. Instead of stopping at 1, I'm going to extend that area over to 2, right? So we're going to add on this little piece and this piece right here, okay? Right? So is that positive or negative?
Positive.
Still positive, right, okay? Because I'm still going from 0 to 2. So the reason that's positive is notice your positive area, right? The part from here to here, I don't know exactly, it's like about 1.5, right? Okay? That positive piece, right, greatly is much larger than the little negative piece right here, okay, from about 1.5 to 2, right? So altogether, this area is still positive, okay? It does have a positive part and a negative part, right? This is the positive part and this is the negative part, but the positive part greatly outweighs the negative part, right? So altogether, this area would still be positive. So we can just see, right, intuitively, that area is going to be positive. All right, now let's make it harder, okay? So let's go from 0, well, I don't know if it makes it harder, but let's make the area bigger, all right? So let's start at 0 here a bit, but now let's go all the way over to 5, which happens to be one of the x-intercepts for this curve, okay? It crosses the x-axis right there at 5, all right? And so let's just shade in that area. And see, you can see here why this integral notation was invented, because it's so hard to draw a picture of these areas, okay? So think about in the 1600s when this process was being developed, okay, by Newton and Leibniz. It's very difficult for them to draw these curves, right? Okay, because they didn't have this nice graphing calculator software like we do, right? Okay, so they didn't want to have to draw these curves all the time, so that's why they started inventing this notation. Okay, all right. Well, nevertheless, is this area going to be positive, or is this big area going to be negative? Yeah, in this case, it's going to be negative, right? Okay, because it's definitely true, right, that the negative piece here is much larger than the positive piece, right? So when you add this area to this positive area to this negative area, you're going to get a negative value, right? So we're sure, we don't know what this area is, but we know it's less than. Definitely know it's less than 0. Okay, let's try one more, and this one's going to be very murky, so we may have to vote here on this one. Let's go from 0 to 6. Okay, so I'm going to have to scroll up a little bit here. So I think, right, there's 6. So we're adding in this piece. And that area is above the x-axis, right? So that area is positive. And so now this altogether, this integral would be this positive area plus this negative area plus this positive area. Wow. What do y'all think there? You think the positive pieces outweigh the negative pieces, or can we tell?
I think it'd break even.
You think, and Zaman says, no, I think it's exactly 0, which is possible. Okay, yeah. It may be that these two areas, these two positive areas add together is exactly the same as this negative area. Okay, very difficult to tell there, right? Okay, very difficult to tell what the case is here. All right. So now you can see, right, why it's going to be important for us to be able to approximate these areas, right? Okay, because our intuition with eyeballing them is going to get, not so great quickly, right? Okay, so I really don't know. How many say, do you think it's positive? But raise your hand high. I can't see if you're just... So it's all together. Is that a positive area? How many think it's a negative area? Well, we're about 50-50, okay? I can't tell there, all right? So maybe Zaman is right. Maybe this is approximately 0, okay? Maybe the positive pieces outweigh the negative pieces. We'll check this if we have time here at the end of the class, and we'll see how close it is to 0. Okay, or if it really was positive or negative. All right, let's try another one. So this one should be, I think, fairly easy for us. Here is a really unusual shaped curve called g. All right, so here's a function g of x, all right? And so g of x is just a straight line to its first x-intercept, which is at 3, okay? And then g of x is a semicircle. So, I can't draw these circles very perfectly, but that's supposed to be a semicircle there. So that's a circular shape right there, okay? Perfectly circular shape, all right? And then g is a straight line again here. On the right-hand side, okay? All right, nice straight line again. And so we want to calculate now this integral. So again, we should be able to use our knowledge of geometry, right? Okay. So I want to find the integral from 0 to 15. The area here beneath the curve, right, okay, to the x-axis, or in this case above the curve, right, to the x-axis from 0 over to 15. So let's shade in that area that I'm talking about here. So it's going to be this piece, right, And so that's very convenient. That's just a triangle, right? And then we've got this piece, which is a semicircle. So that's half of a circle. And so we have to remember a little bit about geometry. How do we calculate the area of circles? Correct. But I think we can do that. And then we have this third piece here, right? Okay. Which, again, that's nice. That's just a triangle, right? Okay. So if I can remember how to calculate the area of triangles and how to calculate the area of circles, then I should be able to compute this. I should be able to compute this integral. All right, let's start with the triangular pieces first, right? Because, well, those are the easiest, right? So let's see. What about this first triangle? We have to know the base times the height, right? So it looks like the base there, that's the horizontal part. So what's that? That's 3, right? Because this x-intercept is at 3. And what's the height? 4, right? Okay. And so we're going to take 1/2 of that. So it's 1/2 times 3 times 4. 1/2 of the base times the height. But remember, this area is below the x-axis, so we're going to count this as what? Negative. So put a minus sign in front of that. Okay? That piece is going to be negative. Okay? So don't forget to do that, or you'll end up with a much larger value than you're supposed to get. Okay? For the total value of the integral. All right, let's do this triangle, because that one also should be fairly easy. So let's see what's its base. So again, that's the horizontal length here. So that's from 9 to 15, which is what? 6, right? And the height there, we'll have to read that. 3, right? Okay, so yeah, 1, 2, 3. Okay, so that goes up to 3 on the x-axis. And then we're going to take 1/2 of that. But this area is positive, right? So I don't have to worry about changing the sign to negative, right? Okay, so this area you're going to add in. And then finally now we've got to remember the circle. Okay? All right, you all remember the formula for the area of a circle? Let me write this down. Area of a circle. Anybody remember that? That perfect, right? Yeah, that's pi. Okay, times the radius squared. That's the area of a circle. Okay, so remember the radius is the distance from the center of the circle to the edge of the circle. Okay, so let's see. For this circle, where would the center be? I think it would be right there, right? Okay, and right there would be the center of that semicircle. And what is its radius? So what's the area from the 3, right? Okay, just count off the units there. It's exactly 3. So the radius of this semicircle is 3. And we're going to square that and multiply it by pi. But that's the radius, that's the area of an entire circle, and we've only got half of the circle here, right? So we have to cut this in half, all right, because we only have half of the circle drawn here in this picture. So again, we'll just multiply here by 1/2. Okay. So there it is. There is our area for. We're stopping at 15. Okay. What when you say the last part? What do you mean? No, I did include it. It's right here. Yeah, okay, right. Yeah, there's the first triangle, that's the second triangle, and then I just wrote them out of order. Yeah, okay. And that is the circle in the middle. So let's see. This looks like it's going to be minus 1/2 times 4 is minus 2 times 3 is minus 6. So this is minus 6 plus this will be 9, right? Okay. 1/2 times 6 is 3 times 3 is 9. And then plus 9 over 2 pi, okay? Because 3 squared is 9 times 1/2 is 9/2. I could write that as 4.5, but I'm just going to write it as 9/2 times pi. And you can get a decimal approximation for pi if you want to. Of course, remember, that's a famous decimal approximation, 3.14159, right? Okay? But we can just leave it as pi here. We don't really have to write a decimal approximation here. But I can add the -6 and the 9 there. That's 3. So I'm going to write this as 3 plus 9/2 pi. So that's the value of this integral. Okay? This negative area and then these two positive pieces added together, 3 plus 9/2 times pi. Okay, all right. So far, kind of easy, right? All right. Well, we got to bump it up a little bit in difficulty. So let's actually think now about how is it that we're really going to approximate one of these areas when the edge, when the function is not, a nice simple curve like a semicircle or a straight line. Okay. So again, what if you have a nice wiggly function, right? What if you have a nice wiggly function here, and you're trying to determine the area there beneath that wiggly curve, right? Down to the x-axis. Okay, how are we going to try to approximate that? All right, so there are lots of schemes, okay, for doing such approximations, but we're going to start with the one that's simplest to describe, okay? What we want to do is, it's a very simple idea. We're going to try to take that area and fill it up with geometric figures that we know how to calculate the area of. Okay? Get the idea? So we're going to take that irregular shape, that irregular area, and we're going to try to fill it up as best we can with geometric figures that we know how to calculate the area of. And then we're going to add up the area of those geometric figures, and that will give us at least an approximate value for that irregular area. Okay? Now, what's the easiest geometric figure to calculate the area of? We could use circles, so I could try to fill up all of this area with little tiny circles, you see. Okay? But it's not that easy to calculate the area of circles, right? Okay, so instead I'm going to try to fill up this area with rectangles, because it's very easy to calculate the area of rectangles, right? Okay, how do you calculate the area of a rectangle? It's just the length times the width, right? Okay, it's just the length times the width. Okay, so what I've done in this picture is I have subdivided here this interval between A and B. I've subdivided it into 5 pieces. Okay, see the 5 pieces there. There's 1 piece, there's 2 pieces, 3 piece, 4 piece, 5 piece, right? And I've drawn a rectangle above each one of those pieces. Okay, I've drawn a rectangle above each one of those pieces up to the curve. Okay, up to the curve. Now, in this picture, I've drawn the rectangle so that the left side of the rectangle, okay, touches the curve. Is that the way I drew this? So I drew this rectangle, and I drew it so that the left side came up here and touched the curve, right? But the right side of the rectangle may not touch the curve, all right, in this picture. It comes pretty close, but you can see there's a little bit of a gap there. But I've tried to draw these rectangles so that the left side of the rectangle touches the curve. So here's another rectangle. Here's my second rectangle. And the left side of this rectangle touches the curve. But notice the right side of this rectangle does not touch the curve. See? You got to make sure you're drawing your rectangle. This third rectangle, I've drawn it so that the right side of this rectangle touches the curve. But, the left side of the rectangle. I'm going to get, my dyslexia is going to come into play here. The left side of the rectangle touches the curve, right? But the right side doesn't have to. So I've drawn each of the rectangles like that. You could have done it the opposite way, though. We could have done it the opposite way so that the left side of the, the right side of the rectangle touches the curve. Okay? So I could have drawn the rectangles differently. And what we'll do is just calculate the area of each one of those rectangles, and we'll add them up, and that will give us at least an approximate value for this area, right? Now, is the approximation going to be exactly correct? No, it's not going to be exactly correct, right? Okay, it's going to be off by a little bit, because notice this rectangle is a little bit too tall, right? It goes above the curve, and this rectangle is a little bit too short, right? It goes below the curve. So we're only going to get an approximate value for this area. We're only going to get an approximate value for this area, but see, here's the trick. The more rectangles I start using, the more I start filling this up with rectangles, smaller and smaller rectangles, then we'll get a better and better approximation. Okay? We'll get a better and better approximation. So here I've only drawn 5 rectangles, okay? But I could have drawn 100 rectangles, okay? Or I could have drawn 1,000 rectangles or 10,000 rectangles, and the more rectangles I've got, the skinnier the rectangles are, but the better approximation I'll get for this area. Now, of course, drawing 10,000 rectangles is not so easy to do, right? Okay, so I didn't draw 10,000. Okay, I only drew 5. That's hard enough, all right? But that's the idea, okay? We're going to try filling up this area with some sort of regular geometric shape that we know how to calculate the area of, add up the area of those shapes, and that will give us an approximation for our area, okay? All right, now that's kind of an abstract example, so let's take a look at a specific example. So let's go back to a specific formula, okay? So x cubed minus 4x squared plus 4x plus 12, okay? And I want to find an approximate value of that, the area between that curve and the x-axis from -1/2 to 1.5, okay? So I think that was the first picture that I drew. Was that the first picture that I drew? Back up here? Let's scroll back and remind ourselves. Oh, it's way up here. Yeah, it is, right? Okay, that was the first integral area that I showed you here, okay? There it is shaded in. So I want to find an approximate value for that area, okay? But I'm only going to get an approximation, all right? I'm only going to get an approximation. So I'm not going to get an exact answer for what this area is. I'm only going to get an approximate value. All right, so let's see if we can do the arithmetic. This is just going to be a lot of arithmetic here, okay? So let's see if we can do the arithmetic here and get this approximate value for this integral, okay? So again, what I'm trying to approximate here is this shaded area, okay? And I'm going to do that by adding up the area of these rectangles that I've drawn. How many rectangles am I using here? What? 4, right? Yeah, just count them, okay? So I filled up this area with 4 rectangles. Now, look, we want to do this so that the rectangles all have the same width, okay? We want to do this so that the rectangles all have the same width, right? Okay? Because it would be kind of silly if we did this so that all the rectangles have different width. That would just make our calculations harder, okay? So I'm drawing these rectangles so they all have the same width. So let's see, what would that width be? Well, let's see. We're trying to find the area from -1/2 to 1.5, right? Okay? We're trying to find this area from -1/2 to 1.5. So what's the total length there along the x-axis? What's the length there from -1/2 to 1.5? 2, right? Okay? And we're breaking that up into how many rectangles? 4. So each one of those rectangles is going to have a width of 1/2. 2 divided by 4, right? That's going to be the width of each one of those rectangles. So I know what the width of each one of the rectangles that I've drawn there is. It's 1/2. Okay? And you need that width, right? Because that's part of calculating the area of a rectangle, because you always take the width times the height. Okay? All right, so in approximating this area, I'm going to have 1/2, right? That's the width times this first height, right? Okay? And then I'm going to add into that, right, 1/2 again times this second height, right? Okay? And then 1/2 again times this third height, okay? And then I'm going to add 1/2 again times the height of this last rectangle, all right? Now, the widths are always 1/2, so that's always very easy. What's different every time is the height of each one of these rectangles, right? Now, how have I drawn the rectangles, though? So I've drawn the rectangles so that which side touches the curve? The left-hand side, right. Okay. So the left-hand side here always touches the curve. And that's going to give me a clue as to what the height of each one of these rectangles is, right? Okay. So let's start with the first one. How can I find the height of that first rectangle? Okay. So I'm trying to figure out what is this height. So that is from x-axis up to the curve. How would you determine that height? Well, unfortunately, I can't just count, right? Okay.
That's like inside, so it would be 8.
Yeah, so what I'm trying to figure out is what is this y value right here on the y-axis? Isn't that what I'm looking for right there, right? Okay, because that's going to be the height. How would you figure that out? Well, look, that's where the curve comes into play, you see, okay? Because the height, notice the height of this rectangle, it corresponds to the output from this function at minus 1/2, doesn't it? Okay, right? You know what the formula for this curve is, right? You know what the formula for this curve is, right? So you can figure out what this y value is just by plugging what into this formula? Yeah, the minus 0.5, exactly right. Just plug the minus 0.5 into this formula, and that will give you the matching y value there, right? And that's going to be the height of this rectangle, okay? In other words, the height of this rectangle, here's how you would indicate that in function notation, is going to be f of minus 0.5. Isn't that correct? Right? You take the minus 0.5, plug it into your function formula. That, by the way, the name of that function was f. Okay? And the matching output you get there is going to be that y value. That is the height of this rectangle. Okay? This one y'all can tell me easily. What's the height of this rectangle?
12.
It's 12, right? Because that is f of what? 0, exactly right. Okay? That is f of 0. See, when you calculate f of 0, you're going to get this matching y value here. And you know, by the way, that happens to be 12. Because when you plug 0 into this formula, all you'll have left is 12. So the height of that second rectangle is 12. What about the height of the third rectangle? How would you calculate that? Plug 0.5 into your formula, right, okay? Just plug 0.5 into the formula and find the matching y value. That's going to be the height of that third rectangle. In other words, calculate f of 0.5, okay?
For the first rectangle,
Uh-huh.
can't you just count up the y coordinates until it'll be like 8.5?
Yeah, it's going to come out something like, it looks like it's something like 8.5, right, okay?
You can just count it up, right? You don't have to plug it in.
No, you have to plug it in, okay? Because, Zaman, this is already an estimate, okay? So if you give me an estimate for what this y value is, you have now estimated twice, okay? So you're going to get a worse estimate, right, okay? But there's no reason for us to estimate twice. Yeah, I think you're right. It's going to be something like 8.5, okay? But there's no reason for us to estimate twice because we can find this value exactly by just plugging the minus 1/2 into the formula, okay? Now, it does take a little bit of arithmetic. I agree with that, okay? So that's not going to be pleasant, but you can calculate this height exactly. All right, what about the last one? What about the height of that last rectangle? So that's f of what?
1.5.
Not 1.5. Yeah, remember, you're always drawing the right side up to the curve, right? I'm sorry, the left side up to the curve, right? Okay, so that's going to be f of 1. Now I have already calculated these, so let me tell you what these values are. Okay, so you can find them though just by plugging these 4 numbers into the formula. Okay, so you could grind through this arithmetic with your calculator, and it would take you. Well, this one's very easy. Okay, these others might take you a little longer, right? But I've already calculated these, so let me show you what those are. This first one is, you thought it was 8.5, right? It's 8.375. Okay, so you were close, but not quite, right? Okay, plus 1/2 times, you already knew this one is 12, right? Okay, plus 1/2 times f of 1/2 is 12.625. Okay, and finally the last one is 11. You already told me that, right? Okay. When you plug 1 into this formula, you're going to get 11. So just 1/2 times this, plus 1/2 times this, plus 1/2 times this, plus 1/2 times this. Add all those together, okay? And that turns out to be, I hope I have this written somewhere, 22? Wow. Okay, so there's our approximate value for the integral, okay? We think it is, this is exactly 22. So we think our area there is approximately 22, okay? But we know it's not exact, right? Because you can see that these rectangles do not exactly fill up this area, correct? Okay? You're missing a little bit right here with this first rectangle, correct? So there you've underestimated a little bit. What about these 2 rectangles? These 2 rectangles are a little too tall, right? Because they go above the curve. So these 2 rectangles have overestimated a little bit, all right? Okay? But probably a fair estimate, okay? At least it's an estimate, right? We're thinking this shaded area, this green shaded area is about 22, all right? Now, again, the question is, how do we get a better area? Use more rectangles, okay? So we only used 4, but if you used more rectangles and smaller rectangles, by smaller I mean they wouldn't be as wide, you could get an even better estimate here, okay, for this area. That's tough to do by hand though, okay, because that's already taxing our calculation skills, right? All right, already doing that with just 4 rectangles. Let's try another one. Here, let's use 6 rectangles, okay? Now, this is a slightly different curve, okay? So this is not the same curve, right? But it's almost the same. It's x cubed minus 6x squared plus 4x plus 5. And I want to estimate what is the integral from 0 to 6. So I didn't shade in that area, okay? I didn't shade in that area. But that was the one a moment ago that we were trying to determine if it was positive or negative. Okay, that area from 0 to 6, right, underneath this function, that was the one we were trying to decide if it was positive or negative, and we couldn't make up our minds, okay? So now let's actually estimate that area using 6 rectangles, okay? The reason I'm using 6 is that's a very convenient number here, because what's the length here of this interval? We're going from 0 to 6, so what's its length? 6. And if you divide that into 6 rectangles, then each rectangle is going to have what width? 1. Exactly right. So we get a very nice width for our each one of our rectangles. Okay? It's always going to be a width of 1. But the height now, of course, is going to be different for each of the 6 rectangles. Now here I drew the rectangles slightly differently. Instead of drawing them so that the right side came up to the curve, I'm mixing this up every time. Instead of drawing it so that the left side went up to the curve, like in the prior picture, I drew this one so that the right side comes up to the curve. You see that? Okay? The right side of each one of these rectangles either goes up or down to the curve. Okay, so I drew these rectangles slightly differently. You can do it either way, okay? So that the left side of the rectangle touches the curve, or the right side of the rectangle touches the curve. And you don't have to use rectangles, by the way. Again, sometimes in approximating these integrals, we use different shapes, okay? But they do have to be nice, regular shapes, because we've got to be able to calculate geometrically the area of the shapes, okay? So rectangles are just so easy to calculate the area of a rectangle. All right, now let's approximate this area now and see what we get, okay? All right, so what is going to be the height of this first rectangle? Okay, so we know its width is 1, right? Okay, and we got to calculate its height. So I drew this one so that the right-hand side comes up to the curve, right? So how would you calculate the height of that rectangle? That would be f of 1, right? You would use f of 1 because the right endpoint of that rectangle is at 1. Right? So it's not f of 0, it's f of 1 the way I've drawn it. Okay? So you take 1 times f of 1 plus 1, because the second rectangle also has the same width. And how do you calculate the height of the second one? What now? Plug in 2, that's right. Okay, there you would plug in 2. But now be careful, because this rectangle is what? Negative, that's right, because it's below the axis, right? Okay, so I don't want to put a plus there. Instead, I want to put what? Yeah, there I want to put a minus. Okay, so that you have to be very careful about, right? Okay, so it's minus 1 times f of 2. All right, what about for the third rectangle there? That's going to be negative again. 1 times f of what? 3, right? Okay, because the height of this one corresponds to 3, right? Okay, on the x-axis, find f of 3. Oh, I made a mistake here. Okay, I don't have to put the minus in this case, all right, because the f of 2 and f of 3 are already going to be negative, right? Okay, isn't f of 2 negative? Yeah, and f of 3 is also what? Negative. So the negative sign is already accounted for in the f of 2 and the f of 3. Okay, so if I put another minus sign in front, I'm going to make it positive. So this you can leave as plus. All right, there's already going to be a minus sign involved there because these things are negative. What about the next one? So that's f of 4, right? Okay. And the next one is f of what? F of 5. Yeah. Yeah, you have a little rectangle right here, but this is kind of an unusual rectangle because it's completely flat. All right. Okay. There is also a rectangle. F of 5, it turns out, is 0. Okay. So you're going to get a completely flat rectangle right there. Okay. And it has area 0. In integration, you can have area 0. Okay. And then what about the last rectangle there? That is f of 6. Okay. Wow. All right. So now you've got your work cut out for you because you're going to have to take 1, 2, 3, 4, 5, and 6 and actually plug them into the formula and calculate these outputs. All right. So you've actually got to plug those in and calculate those outputs. And let me show you what they are, though. So I've done this for you already. Okay. So we're going to have 1 times 4. Okay. Plus 1 times a negative 3. F of 2 is negative 3. Plus 1 times f of 3 is minus 10. Is that what it looked like what my picture shows? Yeah, not bad. A little bit off there, but not too bad. Okay, right? Plus 1 times f of 4. F of 4 is minus 11. Plus 1 times f of 5, but f of 5 is 0, okay, plus 1 times f of 6. F of 6 is the big one. That is 29, okay? This is way up at 29 on the y-axis, okay? So basically you're taking what? 4 minus 3 minus 10 minus 11 plus 0 plus 29, okay, because you're always multiplying by 1. Yeah? The f of 6 is not negative. F of 6 is 29. Yeah, f of 6 is 29. And f of 5 is 0 because 5 happens to be an x-intercept for this curve. Okay? So you get a kind of an odd case here. You get a flat rectangle right there. It winds up having area 0. So that's really going to screw up our estimate, okay? Because we're going to miss this area completely. All right? And when you add all those up, let's see, I come out to what? 9? Is that it? Let's see, 4 minus 3 is 1, minus
29 minus 11 is 18, minus 10 is 8, minus 3 is 5, plus 4 is 9.
9? Okay, well, all right. Anybody disagree with that? Okay. 1, negative 9, negative 20, plus, yeah, you're right, is 9. Okay, there we go. Okay. So we come out with 9, which is positive, okay? So it looks like, at least according to this estimate, we were wondering if that area was positive or negative, right? Okay? And here it comes out positive. But this is really, who knows how good this estimate really is, right? Okay? Because I totally missed this piece, right? Okay? And that rectangle really does not approximate that area very well at all, right? Okay? So that's a really wild approximation. Yeah, you always want the rectangles to be the same width, because otherwise you're going to have to, these numbers will all be different, and that'll really make your life way more complicated. It's already tough because you've got to calculate these output values, right? So if you're using always different widths, it makes it worse. Theoretically, you do not, though, however, have to do that, okay? That's just a practical matter, all right? So we're thinking this is approximately 9. This is on the test, right? It's in your homework, the first integration homework, okay? So you'll get to practice this a little bit. All right. Now, here's what I want to do, though, okay? All right, come on. Actually, in Desmos, I've already got a screen that will do this for us, if this will cooperate. There it goes, okay? Come along, Desmos. Not on the exam. That won't be, we won't be able to do it on the exam, right? Okay? But the great thing about Desmos is, if I can get it to load, oh, there it is, finally, okay? So there is that curve, okay? Now, in Desmos, I can't draw the nice rectangles, all right? So that's not, Desmos can't draw the rectangles. So you just have to visualize the rectangles there, okay, like we had already drawn them. So, but you can set the left limit and the right limit and the number of rectangles, and then Desmos will give you the approximate area, okay? So let's see if we got it right there. There's the, oops, no, this said, this says minus 15. Oh, I know why, okay? Because this is set up so that the rectangles are always on, the rectangles always touch the curve on the left-hand side, okay? And in that prior approximation, I was touching the curve on the right-hand side, okay? Yeah, you get different answers, okay? Well, you don't, all right? You don't know, okay? But here is, but we know that both answers are incorrect, right? Okay? We know that both answers are incorrect. So what we'd like to do is get a better estimate. And how can you get a better estimate? By doing what? Increasing what? Yeah, increasing the number of rectangles. And Desmos will let you increase the number of rectangles as big as you like. So let's start increasing the number of rectangles here. Okay, and so let's go from 6 there. Let's go up to no, I'm going to 6 there. Okay, I picked the wrong place, right? Let's go up to 10. All right, so let's go to 10. So with 10, we got minus 12.12. Right, y'all write these down for me, these values down. So I had minus 15. My first estimate was minus 15. Then I got minus 12.12. Right? Now let's go up to 100. Okay, so let me put a 100 there. And then I got minus 6.7092. Okay, and now let's go to 1,000. Okay, and you get minus 6.071892. And let's put 10,000. And you get minus 6.00719,892. Okay, and let's even put another 0. Let's get really ambitious here and put, wow, how many rectangles am I using there? Yeah, so obviously you're not going to draw 100,000 rectangles, right? Okay, but now we got minus 6.0007. Those numbers are clearly converging to something, right? Okay? What is it clearly moving toward? -6, right? Okay. So that leads us to conclude that what's the right value for this area? -6, right? Okay. So the 9 was wrong. By the way, do I have the right curve in there? Oh yeah, that's the right curve, isn't it?
Pretty much,
yeah. So the right area there was actually, we think, -6. Okay? So that's the trick that we're actually going to use to calculate these areas, is to use more and more and more and more and more rectangles and look at the pattern of estimates, okay? And look at what those pattern of estimates is converging to. All right. Remember, that was very similar to when we were doing a rate of change, right? We were calculating slopes of secant lines and looking where the slopes were converging to. Okay. Well, now we're estimating these areas with rectangles and looking at where those estimates are converging to. And we think, oh, that must be the correct area as we get more and more rectangles. So I think the correct area here was -6. All right. -6. Okay, all right, so that's all for today. Next time now, I'm going to show you two things, okay? Where does this problem occur in practice? Where in practice do we care about calculating the area under a curve, okay? Why do we care about that at all, okay? That seems like it's not just it's kind of an interesting geometric exercise, but in practice, why do we care about calculating the area under a curve, right? What practical application does that have? All right, and then how do we do this efficiently, right? Okay, because we can't be constantly relying on Desmos, right, to give us estimates, right? Okay, so how do we do this exactly without having to rely on with pencil and paper, right? Without having to rely on the computer or the calculator. Okay, all right, so we'll take that up next time. Okay.